Welcome to this presentation called on the time delay estimation performance limits of new GNSS acquisition codes. The goal of this presentation is to present the performance limits on the time delay estimation of new pseudorandom noise families that have been proposed for a new GNSS signal that try to intend to ease the acquisition process. Before to start to talk about the content of this presentation, I would like to present the context. We are talking about the GNSS system where we have a GNSS receiver that is going to be receiving the GNSS signal from a constellation of satellites, and this GNSS receiver is going to try to compute the distance between the GNSS receiver and the satellites. Once that we have the different distance, we will be able to try to solve a geometrical problem where the solution is the GNSS receiver position. Of course, in order to do that, the GNSS receiver has to do what is called the two-step process, which is divided in the acquisition part, where the GNSS receiver is going to detect if there is a GNSS satellite transmitting a GNSS signal. Once that he is detecting this signal, he's going to try to do a rough estimation of the time delay and also of the Doppler. Once that we have finished this acquisition part, we are going to pass to the tracking step, where we are trying to estimate precisely this time delay and also the Doppler. Of course, you can do that for all the GNSS signals, but in this job we are going to try to focus in the acquisition GNSS signals that usually are characterized to have a really simple modulation, like for example the GPSAA that have the BPSK modulation, and also to have a pseudorandom noise families we have desired properties in the autocorrelation function and in the cross-correlation function. Okay, so now that we have presented the context of this job, I would like to present the content. First of all, we will present the signal model. After that, we will present the pseudorandom noise families that have been proposed for this new GNSS signal. After that, we will present the time delay Cramer bound for band-limited signals. Okay, this Cramer bound for band-limited signals differs from the typical Cramer bound used in the GNSS community because this previous Cramer bound is focused just in the power spectral density of the signal. And usually when you compute the power spectral density, you neglect the pseudorandom noise effect. So thanks to this time delay Cramer bound for band limited signals, we are going to compute this formula considering the sample of the signal. And as a result, we are going to consider this pseudorandom noise effect. In order to verify this formula and in order to compute the threshold, we are going to compute the maximum likelihood estimation. Finally, we will present the results and the conclusion. Okay, so first let's present the signal model. We are going to consider a GNSS signal that we are going to denote CT. Okay, that is going to be band limited. It's going to have a bandwidth of B, and this signal is going to be transmitted in a carrier frequency Fc. So now, if we consider the standard narrowband assumption, we have this resection signal that is going to be our signal in the transmission with a delay, and also that is going to be perturbed by this delay and also by the Doppler effect. Now, if we consider the baseband output of the receiver's Hilbert filter, we have this signal xt, okay, that is going to be this signal delayed, of course perturbed by the Doppler effect. Also, we have this attenuation due to the channel, and we have also this complex white Walser noise that is going to be additive to our signal. Of course, we have said that this Cramer bound formula is going to be based on the sample of the signal. So first of all, what we have to do is just to pass our signal from the continuous time to the discrete time. So we are going to compute our discrete vector signal model that is going to have n samples, that these samples is going to depend basically on the sampling frequency, that the sampling frequency is related with the sampling period. Okay, so we have our x that is going to be this perturbation alpha, okay, our vector a, and also our vector that is our noise. This A basically is going to be our transmitting signal, delayed, okay, and perturbed by the Doppler effect. Okay, so once that we have presented this pseudo-random noise, this signal model, we would like to present the pseudo-random noise families for this acquisition GNSS signals. Why they decide to create this new pseudo-random noise that they are optimal for the acquisition? But basically, the goal was to reduce the time to for fix. That basically is trying to reduce the time that we need in order to geolocalize our device. So in order to do that, we need codes that have a really good performance in terms of acquisition. And the idea of this job was to evaluate if this new code that they are optimal for the acquisition part can preserve the time delay estimation performance. So we are going to evaluate three different families. The first family is the gold family. That is pretty well known because actually is the family used for the GPSAA. In any case, the family that we have proposed have several more properties. For example, we have a secondary point in the autocorrelation function that is really close to zero in order to don't have a lock in a secondary peak. We have also proposed the Kasami family, and this family is really close to the gold family because both of them are mathematical pseudo-random noise families. So basically, they are generated based in the polynomial theory. Finally, we are going to focus in the random family. This random family is basically generated by genetic algorithms that they are based in a cost function. This cost function, and this cost function basically is depends only on the autocorrelation function and in the cross correlation function. Basically, this cost function is going to evaluate the difference between the autocorrelation function values and the Wells bound. This Wells bound is the theoretical limit. So any point of the autocorrelation function that is higher or lower than this Wells bound is going to be a loss of performance. So we have seen in the reference paper that this random family have the reason that we are going to focus in this random family. This random family is generated based in the genetic algorithm proposed for the Galileo codes. Basically, what we have is a random set, now is the initialization set, and with this set we are going to evaluate this cost function. After that, we are going to select some flips in the bits, and we are going to evaluate again this cost function. If the performance are better, we are going to accept the flip of these bits. Otherwise, we will refuse this flip. And we are going to iterate this process until the cost function cannot be more minimized or until we have a maximum number of rounds. It's like this that we are going to compute this random family. And this pseudo-random noise family at the end is going to be our CT, our transmitting signal, because we consider just a really simple modulation that is the BPSK. Okay, so once that we have done that, now what we are going to do is just to present this Cramer-Abound formula for band-limited signals. In order to do that, we compute this Fisher information. As you can see, this Fisher information depends basically on the sample of the signal, also of the signal to noise ratio, and also of the sampling frequency. Okay. We would like also to present the maximum likelihood estimation. So basically, this maximum likelihood estimation is going to be able to estimate our time delay based on this formula. That basically is going to be the correlation between the receiver signal and the replica of the transmitting signal at the receiver. Now I would like to present the results. First of all, we will present the autocorrelation function of the goal codes of the GPSAA signal. And we can see that these GPSAA signals they were not optimized for the acquisition part. And we can see that because actually the autocorrelation function is different from the different codes. For example, here we have plotted the autocorrelation function for the satellite for the signal of the satellite 6, 7, and 8. And we can see that, for example, the autocorrelation function of the satellite 8 is thinner, and as a result we are going to have a better Kramer bound. That involves that we are going to have a better time delay estimation. In any case, for our signals, as one of the most important points is to have a secondary point in the autocorrelation function that is close to 0, we are going to have the same autocorrelation function for all our codes. Okay, that does not happen in the case of the GPSA8. Okay, so that was we have presented that. I would like to present now the results considering the surrounding noise families that have been proposed for these new GNSS signals, and this kind of codes that have been optimized for the acquisition part. So basically we are going to compare these surrounding noise families, these surrounding noise codes, with respect to the GPSA signal of the satellite 7 that have this satellite 7 is that one that have the autocorrelation function, the second point of the autocorrelation function close to 0, and we can see here for the gold family, for the Kasami family, or for the random family, that we converge to the same Kramer bound, proving that our codes had exactly the same time delay estimation as the gold family. Also, we have plotted the maximum likelihood estimation, and we can see that the thresholds are almost exactly the same. Even more, we have also plotted we have plotted the Kramer bound for different sampling frequency, and we can see here that if we have a higher sampling frequency, the Kramer bound is going to be lower, and we are going to improve in terms of time delay estimation. And this is pretty good because actually we can try, if we want to improve our time delay estimation performance, what we have to do is basically to use a higher bandwidth. To conclude, I would like to present the conclusions. So basically in this job what we have to do is just to evaluate the time delay estimation for acquisition signals. These acquisition signals try to use these new surrounding noise families that have been optimized for the acquisition step. And the idea was to evaluate this time delay estimation with respect to the traditional gold codes in order to see if we can preserve this time delay estimation performance. As we see, these acquisition signals, we usually use a really simple modulations like the BPSK, and of course this random noise needs to have a really good autocorrelation function and really good cross-correlation function properties. So in order to do that, what we have done is just to compute this formula of the Kramer bound for the band emitted signals, that instead of depends on the power spectral density of the signal, depends on the sample of the signal. So in that case, we can evaluate the performance of the surrounding noise codes. In order to verify this Kramer bound formula, what we have done is just to compute the maximum likelihood estimator, and thanks also to this maximum likelihood estimator, we are able to compute the threshold of the threshold. So basically, we have good news because thanks to this new code, we are able to improve the acquisition stage, but we can say that these new surrounding noise families preserve also the time delay estimation performance with respect with the traditional gold codes. So thank you very much.